In this lecture, we will discuss the properties of water. So, we have discussed ionic bonds, covalent bonds, and hydrogen bonds. We've talked about polar versus nonpolar covalent bonds. Water is almost always our classic example of a polar covalent molecule. It contains polar covalent bonds. So we have discussed how the oxygen molecule has a very high electronegativity and it pulls those electrons very close to the oxygen itself, while hydrogens are very weak, and so all the electrons are way up here, so we're left with a partial positive charge on each hydrogen, and our oxygen gets a partial negative charge. We then went on and said that these partial positives and these partial negatives are really good for making hydrogen bonds. So partial negative of one oxygen from the water molecule is attracted to a second water molecule, but that attraction would be between the oxygen of the first molecule and one of the hydrogen atoms of the second molecule. So the partial negatives and the partial positives are attracted. Okay, it is a weak attraction, and we said that is our classic hydrogen bond. So why do we keep talking about water? Well, not only is it our classic example of a polar covalent bond, but water itself is also our universal solvent, or our primary solvent. So our body, the majority of our body is made of water. Okay. Water not only is a polar covalent molecule, which is great when we're talking about bonds, but it's also useful for other things. Okay, so first of all, water has a very high heat capacity, which means water resists a change in temperature. So the formal definition of heat capacity is how much heat it takes to change the temperature of 1 gram of water by 1 degree Celsius. And that's very sciencey and it might not mean a whole lot to you, but think about the last time you tried to boil a pot of water to make pasta or tea or whatever it is you were trying to make. It probably took a long time to boil. And if you were in a hurry to make your tea or your dinner, then that was probably annoying. But in our body, this serves a very important purpose because we are exposed to different temperatures all the time. Sometimes it's cold outside, but sometimes it's hot outside. And we don't want our bodies to overheat. And so all of the water inside our bodies, it's able to contain a lot of that heat without necessarily changing our body temperature a whole lot. And so think of how much heat must be within our bodies if we do have a fever, if we have gone ahead and changed our own overall body temperature, how much heat would that have taken to change from that 98.6 to that 99.6 or that 100.5, whatever our new fever temperature is. It took a lot of energy, heat energy, to make that change happen because all of the water in our body was doing its best to resist that change. Water also cushions our body, okay, especially in several of our vital organs. We have intracellular fluid. Hopefully it will not shock you to learn that intracellular fluid is found within the cells. Okay, sometimes you will hear it termed cytosol. Okay. And then we have extracellular fluids. Again, hopefully it will not shock you to learn that extracellular fluids are found outside of the cells. Now, extracellular fluid comes in a few varieties. We have interstitial fluid, which you find outside of your cells, in between your tissues. Okay, things like that. And then, for example, plasma is found within the blood. It's the fluid part of the blood. We have a couple of additional extracellular fluids, but these are our two main examples. Here we've got our little image showing you the difference. So the dotted lines represent a blood cell. So inside of the blood we have the plasma. Okay. And then outside of the blood cell, or excuse me, the blood vessels, we have the interstitial fluid, okay, And then inside the cells themselves, we have our intracellular fluid. So these terms are going to come up a lot in the different body system chapters, things like that. So ICF, ECF, okay, those abbreviations are going to come up more than once, so just make sure you're familiar with those. Okay, so since water is our universal solvent, okay, what does that mean? It means we are able to dissolve things in the water in our body, so we can make a solution. Okay, so solutions have two parts. We have solutes, which are what is being dissolved in the water, and then the solvent is what is doing the dissolving. So if we're talking about inside our bodies, then the solvent would be the water itself, and the solutes would be anything that is dissolved into that water. Now, we could do this in two ways. We can make a solution, or we can make a suspension. Notice in a suspension you see all these little dots. Okay, all these little dots are the solutes that we just talked about. So what you can't really tell is that many of those solutes are dissolved. Okay, many of them may not have dissolved. They're very unevenly spread. Okay, and if we took a suspension in a glass, for example, and just let it sit, eventually all of those little particles would settle out to the bottom. Okay? A solution doesn't work that way. Notice that we don't have any little solutes. Okay? You can't see them. They are very evenly spread. They are very well dissolved. If you let this beaker sit, you will have nothing settle out to the bottom. Okay? Why do we care about suspensions? It's just nice to mention because your blood is a suspension. Okay, so we do have certain dissolved particles in the plasma, but then you also have the red blood cells that do not dissolve, the white cells that do not dissolve. And if you were to take a sample of blood and let it sit, okay, your red cells and your white cells, your platelets would all settle out to the bottom, while you would still have some dissolved solutes in the plasma. Okay, if we were to dissolve glucose in water, okay, if you let this sit, then those glucose particles would not settle out to the bottom, because this would be a solution instead. They're all very evenly spread out. Now, a couple more things about water and we'll be done. Water is only able to dissolve solutes that have similar properties. So we call these hydrophilic solutes. Okay? So water can dissolve solutes that are either fully or partially charged. Okay, there's a term, there's a statement that says like dissolves like. Okay, so if we think about the properties of water, anything that is like water will dissolve into water. So what do we know about water? We know that it has the partially positive and the partially negative ends of the water molecule. So those partial positives, those partial negatives are able to dissolve other molecules that also have positives and negatives, be them full charges, okay, or just additionally other partial positives and partial negatives. So any kind of ionic solute, okay, any of the electrolytes that we've mentioned, the sodiums, the chlorides, the potassiums, etc. Okay, anything that is a cation or an ion will fully dissolve into water, or anything that is also a polar covalent solute, okay, which again, water is a polar covalent molecule, so any other solute that is polar covalent, like glucose, for example, will also very easily dissolve into water. Again, these are all termed hydrophilic solutes, hydro meaning water, philic meaning like or love. Okay, so we love the water. If you love the water, you're going to dissolve into the water. Not everything loves the water. Okay, so if your solute instead is hydrophobic, okay, so water fearing, okay, you are not going to dissolve into water. These are solutes that do not have fully or partially charged ends. Oops, go back. Okay, so no partial positives, partial negatives, no full positives, no full negatives, no anions and cations here, no polar molecules. These would be uncharged, non-polar covalent molecules. Okay? You are already familiar with some of these. These are oils, these are fats. Anything that you can think of off the top of your head that does not dissolve in water is a hydrophobic solute. So the oils that you cook with, okay? Think about what happens if you put butter in water. They do not dissolve into each other. Oil and vinegar, okay? They do not dissolve into each other, okay? There we go. Cohesion and surface tension. So, since the water is capable of making hydrogen bonds with additional water, we have the property of cohesion. Okay, so water molecules stick to other water molecules. See, look y'all, they're in love. They love each other. Okay. Because water is polar, it also tends to stick to other things that are polar, so other stuff. This property is termed adhesion. Okay. Because water sticks to water, and sometimes water sticks to other things, so the cohesion and the adhesion. Okay. These together can create surface tension, which means the surface of a body of water. Okay. There's a little bit of tension there. Okay, it can support a little bit of weight. So sometimes if you have tiny bugs, okay, or other tiny organisms, they can actually float on top of water without, quote unquote, breaking the surface tension, and they will sit on top of the water instead of falling through the water. Okay. That concludes our discussion on the properties of water.